Hi everyone, this is Mr. Cervone. Welcome to my channel. In lesson 87, we will be learning about the lengths of tangents and secants within a circle. So according to the do now, the rim of a car is shown in the figure to the right. To calculate the distances and forces of the rim supports, the engineer draws chords AB and CD intersecting at point E, such that chord AB is perpendicular to chord CD. If the length of segment BE is equal to 16, the length of segment DE is equal to 4, and the length of segment AD is equal to 5, compute the length of segment CE. Okay, so let's analyze this a little further in a circle, as shown. So we know that according to the theorem that we have learned in class, if two chords intersect in a circle, then the product of the pieces of one chord is equal to the product of the pieces of the other chord. So what does that mean? That in this case, if you take the length of segment CE times the length of segment ED, that is equal to the length of segment AE times the length of segment EB or BE. Okay, so we know the length of segment BE. Do we know the length of segment AE? Well, if you look at the triangle ADE, that is a right triangle. We know that one of the legs is 4 and the hypotenuse is 5. So therefore, the other leg, AE, has to be 3 because we know it from the Pythagorean theorem, or we know from the 3, 4, 5 triangles that the legs have to be 3, 4, and the hypotenuse has to be 5. Okay, so let's call CE x. So that means that we can rewrite this as x times 4, because we know that ED is equal to 4. Well, that is equal to 3, because AE is equal to 3, times BE, which is equal to 16. Okay, so how do we find the value of x? Well, instead of multiplying 3 times 16, I recommend to work with smaller numbers. We can, for example, divide 4 on both sides of the equation. So if you divide both sides by 4, you get x is equal to 3 times 4, which leaves us of x value of equal to 12. Okay? So that means that in this case, we found the answer for the do now. CE has to be equal to 12. Okay? So there you go. That is the answer. So here we were just able to calculate the pieces of lengths of two intersecting chords. Let's look at an example in which we do not have chords, but in which secants and tangents are involved in terms of their respective lengths. Here's a problem. Well, according to the problem, the length of segment PB is 2. So let me write this in, 2. The length of segment BC is equal to 6. What is the distance from P to A? So let's keep in mind that segment PBC is a secant and segment PA is a tangent. So the question is, how would you find the length of PA? So here we do not have a formula that gives us the length of PA. So we somehow have to now generalize this. Okay. So let's say we have the following, okay? How do we find the formula to find the length of segment PA in terms of PB and PC? So the first thing you want to do is draw chords AB and chord AC. How is this useful? Well, maybe we can somehow find similar triangles in here. If you look closely here, we know that this angle here is an inscribed angle, okay? So we can write that the measure of angle ACB is an inscribed angle. And how's that related with the intercepted arc? We learned in class that the measure of angle ACB has to be equal to 1/2 the intercepted arc. In this case, it's arc AB. So let me write this down. Is equal to 1/2 measure of arc AB. Okay. Similarly, if you look at angle PAB, this angle, that angle is created by a tangent and a chord. And we also learned that the angle created by a tangent and a chord is equal to 1/2 of the arc that it intersects, which means that the measure of angle PAB is equal to 1/2 the arc that it intersects, which is the measure of arc AB as well. In this case, since both of these are equal, we can now substitute and say that the measure of angle ACB is to be equal to measure of angle PAB. So they're equal in measure. Therefore, angle ACB is congruent to angle PAB by the definition of congruent angles. So here we already have one of the angles that is congruent in both triangles. Do you see any other angles that are congruent? If you look closely, angle P is congruent to itself. So let me write this. Angle P is congruent to angle P. And there you go, we have another angle. So the question is, which triangles are similar now by the a.a. similarity postulate? Well, from the diagram, we can say that triangle PAB is similar to triangle PCA by the a.a. similarity postulate. Okay, now that we have two triangles that are similar, we can generate a proportion. And the proportion has to involve segment PA, PB, and PC. Basically, if you look at segment PB over the corresponding side. So if you look at this is PB, the corresponding segment is PA. So we're going to write PB over PA must be equal to, and here we have, let me select a different color so you guys can see it better. So here we have PA over here, PA, and the corresponding segment is PC. Okay, so let's write that in. So here we have PA over PC. So what is the reason for that? Well, it's simply the following. Corresponding sides of similar triangles are proportional. Okay, so then now that we have developed the proportion due to the similarity here, all we need to do is cross multiply this. And here we have PA squared is equal to PB times PC. And what is the reason for that? So the reason for that is that in a proportion, the product of the means is equal to the product of the extremes. So this is the reasoning for that. Okay, so we just developed the formula here. There you go. That PA squared is equal to PB times PC. So if we go back to the do now, we can easily solve for PA. Okay, so here we have PA squared equal to PB times PC. So let me rewrite that. PA squared is equal to PB times PC, which means that PA squared is equal to PB, which is 2, times PC. Well, we know that BC is 6, PB is 2, so that means that PC is equal to 8. Therefore, PA squared is equal to 16, and PA has to be equal to 4, okay? So we're just taking the absolute value here, the positive or the principal root, which is just 4 because we cannot have a negative number for segment PA. Okay, so that is the answer. Okay, so what happens if you have two secants or two tangents? Is there a relationship between the pieces of the segments? Well, let's discover that. Okay, so here's the discussion for you. or something to think about. What is the relationship between the pieces of the secants or tangents in the figure shown above? So the way you prove it is as follows. Let's look at the first case where you have two secants intersecting in a circle outside of point P. There you go. So in this case, what we want to do is draw a segment from B to D. Okay, and then we want to draw another segment from A to C. As you can see, we have two overlapping triangles here. Triangle PBD and triangle PCA. Can we say anything about the angles? Okay, first we can say that angle P is congruent to itself. Then we also know that angle PBD over here, that angle is congruent to this angle. Well, why is that? Why are these two angles congruent? Well, because they both intersect the same arc over here, arc AD. And we learned it that if two inscribed angles intersect the same arc, then the two angles must be congruent as well. Okay, so now we can apply the a.a. similarity postulate again and state that triangle PAC is similar to triangle PDB. And that's the a.a. similarity postulate. That is the reason for it. Okay, now that we have two triangles that are similar, we can again generate proportion, which is PA over PD is equal to PC over PB. Again, we stated the reason before, which is over here. Corresponding sides of similar triangles are proportional. So let me copy and paste it over here. Okay. So now we can cross multiply this and state that PA times PB is equal to PD times PC. And that is the same reason as before. In a proportion, the product of the means is equal to the product of the extremes. Okay, so now we have a formula for the case when we have two secants. Okay. Let's look at the last case when we have two tangents. Okay, so here we have a circle with two tangents meeting at a point P. Well, do we need to find any similar triangles at this point? Well, not really, because there's a theorem that we already learned. Remember which theorem we're talking about? The theorem goes as follows. If two tangents are drawn from the same circle to the same point, then the tangents are congruent. Thus, we can say here that segment PA is equal to segment PB. Okay, so these two segments must be congruent. And we actually also proved this particular theorem as well by constructing two triangles and prove the triangles congruent by the HL theorem. And then by corresponding parts of similar triangles, the two tangents are congruent as well. Okay, that is the last formula for the third case. So let's summarize here. Here we have a secant and a tangent. So in the secant and the tangents, we have PA squared equals to PB times PC. Then the next one, when we have two secants, we have PA times PB equal to PD times PC. And for the last case, we have PA equals to PB. Well, is there a simple way to remember this? And the answer is yes. And here it is. Basically, all you need to remember is the following. That the outside times the whole, so let me write this down, that the outside times the whole is equal to the outside times the whole. But what does this even mean? Well, let me explain to you what this means. let's say you have a circle. Let's look at the first case. Let's say you have a circle, and let's say you have two secants, okay? So let me draw the secants really quick. Here's the first secant, okay? Then you have the second secant. Okay, so that means that this piece here is considered the outside, okay? And this piece is considered the whole. Similarly, we have this piece on the bottom that is considered the outside, and this entire piece is considered the whole, okay? So if you go back here, let me put the segments here. So we have PAB and DC, okay? So basically we have P, here we had A, here we had B, and here we had C, and here we had D. The formula that we developed was over here, PA times PB. So let me write this down, PA times PB is equal to PD times PC, okay? So basically, PA is considered the outside piece of the secant. And if you look at PB, that is considered the entire piece of the segment, or the whole piece. And if you look at PD, well, PD is considered the outside piece of the segment, and PC is considered the entire segment, again, the whole segment, okay? So basically, you're multiplying the outside and the whole equal to the outside times the whole of the other secant, okay? Well, does this apply also for a tangent and a secant? Well, let's look at it. So let me draw another circle here. Okay, let me put the circle a little bit here. Okay, so let me draw a tangent. Okay, so here's a tangent. And here, let me draw a secant, okay? Okay, so here we had P, this was A, and if we look up here, we had B and C over here, okay? So we write B and C over here. So according to what we obtained before by similar triangles, we had PA squared equal to PB times PC. Okay, so let me rewrite that as PA squared equals to PB times PC. Well, how can we apply the outside times whole equal to I times outside times whole in this case? Well, if you look at PA, that's a tangent. That is considered the outside, and it's also considered the whole segment. So you can rewrite PA times PA equal to PB times PC, okay? So again, PA, this piece is considered the outside, but it's also considered the whole segment, okay? Okay, so let me write this here. Maybe I should use a different color here. So here we have the outside and also considered the whole, okay? And in this case, PB is the outside, and the entire segment PC is the whole. Okay, which means that PB is considered the outside, and PC is considered the whole. Okay, so it works here as well. Okay, what about in a tangent case? Again, we have a circle with two tangents, okay? There you go. So let me draw the two tangents here. All right, so this is P, this is A, and this is B. Why is it true that PA equals to PB? How can we explain that with the outside times whole equals to outside times whole? Okay, so let's do this. Here we have the outside is PA, times the whole is also PA. So this becomes PA squared equal to outside PB, and the whole is also PB, so it's PB squared, okay? So it's basically saying that PA times PA is equals to PB times PB, okay? Which means that this part here, that is the outside. So let me do this again in a different color. So that is the outside, but it's also considered the whole. And similarly, this is also the outside, but also considered the whole segment, okay? Which means that this is called outside times the whole. Okay, so let me erase that arrow. There you go. Equal to, and PB is the outside again, times the whole. Okay, over here. Okay, but since we have PA squared equal to PB squared, that just simplifies to PA is equal to PB, and we are done, okay? So basically, the only thing I want you to remember is that the outside times the whole is equal to the outside times the whole. And this is really the most important of today's lesson, okay? So every time you have two intersecting, or I should say if you have a secant, two secants, two tangents, or secant and a tangent, merging from a point outside a circle, intersecting the circle, all you need to do is calculate the outside times the whole equals to the outside times the whole. Okay, so let's summarize this lesson with an example, okay? So let's say we have the following. It says here, calculate the value of x. Here we have two secants. We know AB is 11, AC is 11 plus 9, okay? So we have EC is 18. How do you find the value of x? So at this point, if you would like to pause the video and try it out, go ahead. Okay, so let's go back to this. So according to this, we have outside times whole is equal to the outside times the whole. Okay, so if you look at the first segment or the first secant, ABC, what is considered outside? Okay, so we have BC is considered the outside of the segment times, and the whole segment is considered segment AC, okay? Equals to, now we look at the other secant, secant EDC, the outside is CD, and the whole is segment CE, okay? So now all we need to do is substitute. So BC is equal to 9. AC in this case now is going to be 11 plus 9, okay? So that's very important to add those two pieces, and that is equal to CD. So we know CD is what? Well, if you look at the picture, the entire segment CE is 18, so therefore this piece CD here is 18 minus x, okay? So we're going to write 18 minus x times CE, and we know that CE is equal to 18, okay? So there are already a few things we can do here. For example, we can divide both sides by 9 and add 11 plus 9, okay? So here we have 20 is equal to, well, if we divide 18 by 9, we get 2, and in parentheses, 18 minus x, okay? Then we can divide both sides by 2, and we get 10 is equal to 18 minus x, okay? So let's say we add x on both sides. So we end up with 10 plus x is equal to 18. And then finally, we subtract 10 on both sides, and we get x equal to 8, okay? Which means that the segment from D to E is equal to 8, okay? Well, at this point, it's also good to ask, well, does this make sense? Well, let's see. If this is 8, if x equal to 8, that means that 18 minus x, that should be 10, okay? If I were you, I would also perform a quick check. Is it true that 9 times 20, okay, in the first sequence, is it true that that is the same as 10 times 18? Well, let's check. 9 times 2, that's 18. And we add a 0 because 9 times 20 is 180. Equal to, and 10 times 18 is 180. So that actually works, okay? So that is the check. Okay. So at this point, I'm basically done with the lesson. What I want you to do is please go to Schoology, work on the worksheet, or the homework assignment that I will be posting. If you have any questions or comments, please go to the comment section of this YouTube videos, and I will try my best to respond as fast as I can. And please don't forget to subscribe to this video. And again, thank you so much for watching. Have a great day.